So my topic is why data compression is important and fun. My slides were made for a little bit smaller whiteboard, and the words important and fun simply did not fit. Both lossy and lossless data compression are fun. I will talk more about the area of my expertise, lossless data compression. As you probably know, typical lossy data compression systems make use of lossless compression at the end. Here's a trivial example of a lossless data transform and a trivial example of a lossy data transform. Swapping bits is reversible, discarding is not. So why fun? First, you can win cash in data compression competitions, as I did a few times, see Hutter Prize, for example. Next, I'd say there's a delightful zoo of lossless compression methods, and many of them were discovered just recently. For example, methods based on asymmetric numeral systems a dozen years ago, and even the Burroughs will transform just 20-something years ago. How do you know whether you can invent yet another method until you try? You should try to invent data compression methods to see how fun this is, and whether you have enough luck, expertise, and imagination. You will very likely learn a lot and have lots of fun in the process. More often, the typical data for your algorithm is either provided to you or picked by you, and the case with test data is even more fun because you can try to model how your test data were generated, and then find transforms that improve performance of the next compression steps, which are usually called context modeling and entropy encoding. Here are my top 3 most interesting tips about transforms. Typically, they are simple, more or less. Their implementations run fast. But it is usually a set of transforms that gives you a competitive advantage against the existing algorithms, both general purpose and rather specialized. And 3, such transforms don't have to reduce data size. They can even increase size of data as long as further compression steps run better on transformed data. For example, switching end-of-line markers in a text or HTML file from Unix style 1 byte to Windows style 2 bytes increases uncompressed size, but in many cases may reduce compressed size. Why are compression methods so different? Context modeling methods assume elements of data depend on context somehow, and entropy encoding methods assume they are independent. Also, some compression methods assume data are quantitative, like samples, while other methods assume data are qualitative, like symbols. And my experience says this is the most important distinction. Also, some methods may work given a few bytes at a time, that is, with seemingly infinite streams, while other methods need a block of data to start operating well. For example, Burroughs Wheeler transform is barely competitive on blocks smaller than 10 kilobytes, while copy-paste methods, the so-called LZ77 family, can compress 5 bytes and then wait for further input. DCT, discrete cosine transform, as used in JPEG images, uses blocks of 64 pixels. They become visible when compression ratio gets too big, 64:1 or more. Why is data compression important? First of all, the vast majority by volume of modern internet traffic is compressed data. By the way, it's very likely that interstellar communication between technologically advanced civilizations, if they exist, is also usually compressed. And compressed data look like random noise, even if produced by a rather simple compression algorithm. Second, almost all of the video you watch is decompressed video. The vast majority of images you see on tablets, phones, laptops, and desktops are decompressed images. You understand the world better once you learn the fundamentals of how they are compressed and then decompressed, and why, for example, you should not convert photographic images to PNG format, black and white scans of documents to JPEG format. In particular, PNG tries to compress output of a filter, which is pretty noisy in case of photographic images, with a copy-paste algorithm. That's why PNG performs so miserably on photographic images. See, for example, lossless photo compression benchmark. By the way, 4 image codecs written by me are on the Pareto frontier in the lossless photo compression benchmark, and you can see what Pareto frontier is and how it works for English text compressors in the large text compression benchmark. Advanced data compression methods can be used to measure descriptive complexity of a file and similarity between files. Descriptive complexity of a block of data, often called Kolmogorov complexity, is defined as the length of the shortest computer program in a predetermined programming language that produces this block of data as output. Interestingly, you can easily compute an upper bound for the descriptive complexity, but computing the lower bound is only possible for a fixed decompressor code and only by brute force, that is by an exhaustive search. In general, it is not possible. You can't say you have hit the limit, except on very small files. I'm sure all basic data compression methods will prosper and find new important applications in future for many reasons. For example, our resources in the material world are always limited. Also, both compression and decompression of seemingly random data can help you see how random it really is. By the way, for me personally, it's important that highly complex compression methods cannot be used in deadly weapons, only the rather simple compression methods. This is run-length decoding of pseudo-random data. Here's a couple of practical advices for those who want to win cash in data compression competitions. First, try to find fast and simple transforms that improve significantly the work of the context modeling methods that you picked. And second, for deeper understanding of data and your compression algorithm, you should create and utilize various graphs and plots, visualizing not only the data you compress, but also the internal data produced by your algorithm, your intermediate data. Let's have a look at a couple of next big achievements for our civilization that might be strongly connected with the concept of descriptive complexity. Disclaimer, what I say further in my talk is speculative, often very speculative. First, let's call it standard model of psychology, a rather compact model that will be will serve as a basis for theories able to predict pretty well a lot, from choice of profession and political preferences to interpersonal relations. Why are astrology and MBTI so popular? I think they try to occupy the empty spot where we must have the standard model of psychology. Questions to the audience. How many people here are familiar with MBTI? Please raise a hand if you are. Second question, and how many have heard of the Big Five personality inventory? Thank you. Third and last question, how many of you know that there are correlations between 4 MBTI scales and 4 of the Big Five personality constructs? Okay, good. Well, there are correlations and they are rather strong, so maybe what MBTI and Big Five are trying to explore is somewhat similar, but what could it be at the core? Psychology has no answer yet. How could descriptive complexity or data compression methods be involved? First, when you try to pack as much information as possible into 4 bits, as MBTI does, this is a lossy data compression process. How much personality how much data about personality of a normal, healthy human do you discard when packing all data into 4 bits? Most likely much more than 50%. But how many bits would you need to achieve 90% accuracy, predicting previously unseen behavior in specified circumstances? Most likely, I would guess not more than 30 bits. Note the standard model of psychology can hardly be used in a deadly weapon, but it can be used as a strategic weapon. Okay, what could the most valuable bits describe, except gender, age, things like that? If at least some of the data processing principles are applicable to data processing in humans, then more likely those are the most fundamental principles. One of the data analysis core concepts is that the variables are either categorical or numerical. Categorical are non-comparable and numerical are comparable. The most important types of data, as far as I know, are quantitative, where elements are, let's call them samples, and qualitative data, let's call the elements of qualitative data symbols. Samples need only a couple scales and a source type to describe them. For example, are they coming from an audio source, a visual source, a temperature indicator? And symbols need a reference to something bigger, like, for example, an ASCII table. This something increases descriptive complexity. But when you create symbolic symbols and when you introduce new symbols, you normally reduce descriptive complexity a lot more, and thus this is kind of a data compression process. By the way, executable code clearly must contain symbols. It can't be made of samples only. The other biggest difference between cognitive functions of humans could be that there are functions responsible for the inner reality, like your senses and feelings, and for the outer reality, with things like human language, logic, imagination, perhaps intuition, and so on. Thus, we can construct 4 cognitive functions, and maybe they somehow correspond to the functions explored by Carl Jung and named sensation, feeling, thinking, intuition. Or maybe there's something similar but different. Anyway, if you arrive at a model with, say, 5 cognitive functions, there must be an explanation why the set is complete, why there are 5 of them rather than 4 or 6, okay? Another big item on our civilization's roadmap is the ultimate nature of reality. How could reality be finite in time or space? Are elementary particles really indistinguishable and fully described by a handful of numbers? What could that mean? Is it true or not that all mathematically possible universes are equally real? If not, is only one of them real? Why? What do laws of quantum mechanics actually tell us about reality? A model of the ultimate nature of reality must explain why some events happen and become reality while other events don't, even if equally probable a priori. Hypothesis that reality at the bottom level is a huge computational structure is discussed in details in, for example, Max Tegmark's book, Our Mathematical Universe. Better understanding of the ultimate nature of reality is highly important for sciences that study the core universe laws like physics and cosmology, but also for many other sciences, including biology, genomics, and even psychology, because it's possible that human genome knows more about the ultimate nature of reality than our civilization. It's very possible that our genome makes practical use of effects that we are not aware of yet. Also, don't forget that bacteria are ubiquitous in every human body, and the sum of their genomes is orders of magnitude more complex than the Homo sapiens genome alone. How could descriptive complexity be involved? Well, if it's true that reality, after all, is a huge computational structure, then time could be the measure of change in descriptive complexity. And then the Big Bang point could correspond to the seed of our reality, a structure so simple that it could be fully described with a few million bits, or maybe even a few thousand bits. As we know, entropy of a closed system never decreases over time, and descriptive complexity is well related to the thermodynamic notion of entropy, so why not? The age of our universe would be the distance to the seed in a tree of computational structures, such that every child structure is separated from the parent structure by a quantum of time. And it is usually bigger than the parent in terms of descriptive complexity, but all structures in the tree contain the same core. Can you imagine something a bit similar to Conway's game of life, but a billion times more complex? First of all, not two-dimensional, not completely deterministic, and very likely not binary. Humans are self-aware substructures in these huge computational structures, substructures of a relatively small size, and that's probably the main reason why we don't experience all child structures of a parent structure as equally real when a split happens. The splits look for us like totally random input into our reality. Because each structure has a finite descriptive complexity, it has a finite number of child structures. On one hand, just one path in the infinite tree is a reality for each of us, but on the other hand, from a human's point of view, the vast majority of paths are observationally indistinguishable. Just like many nodes with the same timestamp are observationally indistinguishable from a human's viewpoint. This hypothesis provides a lot of questions. I can try to answer some of them after my talk. Thank you.